Let's talk about transformers. Transformers was a key component in order for AC power to become viable, and we'll get into why. So ultimately, for a transformer, I got two sets of coils with a different number of coils. This will have N sub P turns, P for primary and N sub S for secondary. And so we have a primary current coming in, going around the loops. The change in the current here will create a change in the magnetic field, which induces a current over here. The symbol that you see in a circuit would look like that, where you basically have a bunch of little bumps there, which represent the coils with a line in between them. Now, in terms of actual mechanics of it, I sort of sketched out 4 different varieties here. The big transformers that you see at power plants or on power poles will look like this, or this basic structure. Usually there's going to be a much greater variant in the ratio of coils. But just so long as that the magnetic field created by one is affecting the other one. Now in this one, the transformer core right here allows the magnetic field that's created here to, in essence, go up over here. It sort of acts as a magnetic field guide. You could also have them overlapping like this, and in a lab, this is sort of where we are going to do it. Or actually, I have a lab that does it that way, and I have a lab that does it this way, where I've got an inner core and an outer core. And then over here, you might see this. This is known as the single-phase topped auto transformer, where you have a number of coils based upon where the connection is. So you have a primary side and a secondary side. Something like this allows you to be able to get a lot more voltage out of a 12-volt battery. So when you crank it, you use something like this in order to increase the amount of voltage in order to get enough power ultimately to start a car. All right, so the math behind it, we have energy is conserved. So the energy lost by the primary coil has to be the energy gained by the secondary set. And so likewise, if we look at the energy used per time, we have power. So the power used by the primary has to be the power gained by the secondary. So ultimately, it's the power of the primary is equal to the power of the secondary. And this is a nice ideal situation. I did read one place that there's about a 1% loss if the transformer is well designed. Power is equal to current times voltage, and so set that up. And then the voltage is related to the change in the magnetic flux. And so I am setting this to, this term right here deals with the change in the magnetic flux for one coil, and then I have that number of coils, and so each one is producing this change. And we end up with the current of the primary times the number of primary turns times this change in magnetic flux. For the primary, for a single coil, the primary is equal to similar for the secondary. Now, since the change in the magnetic flux is the same, heading back over to the other drawing. So as we get a change in the flux here, that change in the flux shows up over on this side. So these terms will cancel out, and we end up with this relationship here of current and number of turns. And so we have the current of the secondary is equal to current of primary times this ratio of coils. Now if we take this equation right here and plug it into that equation, as is mentioned over here, so we have the current of the primary times the voltage of the primary is equal to the current of the secondary times the voltage of the secondary. We have a formula here for the current of the secondary, so we plug that into this, and this is the current of the secondary as found out in equation 2. And we get rid of the current of the primary, and we end up with this relationship right here. So now we can change voltage depending upon the ratio of coils. So if I have 5 coils in the primary and I have 10 coils in the secondary, I'm going to double my voltage. So let's take a look at why this is important. So the power loss will be the current times the voltage through the lines, because wires have resistance. The voltage is equal to current times resistance, and so the power is equal to I squared R. If the voltage and the current are AC, which is what we've been working with. Which value should you use? Well, you use the RMS value, and this is sort of an average value. It's a root mean square value, which is a way of averaging numbers that are both positive and negative, and shows up in another video where I resolve that. So we end up with, so the amount of energy loss is equal to the RMS current squared times the resistance. Now the resistance we can play with, that's based upon the physical nature of the wire, and I address that on the next page. But since we have this relationship as found on the previous page, the number of primary turns over the number of secondary turns is the voltage, primary voltage over the secondary voltage, which is the secondary current over the primary current. That means that the bigger my secondary voltage is, the smaller my current is. And if currents get smaller, the power loss is smaller. And so this gives us a way of really cranking up the voltage in order to reduce the current, in order to have less loss. And with DC, because it is only in one direction, it's a lot more difficult to do that. Alternating current is moving back and forth. We have a continual changing of voltage, whereas DC, at least when it was first being discovered, was basically flatlined. Now, with current technology and current thinking, DC voltage is indeed in one direction, but now it goes like this. So we do still have that continual change of DC. Only Edison had thought of that. Now the controversy is you really have these high voltage power lines now because you crank up the voltage in order to reduce the loss, and it does create electromagnetic radiation. So the question is, does it cause cancer? And the secondary question is really, is it ionizing radiation? Because when radiation comes in and it hits a molecule, if there's enough energy, it's going to knock an electron off, for example. Knock an electron off, which now you have an ion, and if I have an ion, it's free to connect with something else. Now, it takes energy in order to be able to knock an electron away to create an ion, and the frequency of the high voltage power lines is still 60 hertz. It's oscillating back and forth 60 times, and 60 hertz is a low energy radiation. The energy of radiation is equal to this Planck's constant, which is 10 to the negative 34th, somewhere in that ballpark, times the frequency, which would be 60. And so we have this really low energy. With that kind of low energy, it's very difficult to get an electron kicked loose. Now, not saying that it's not impossible, I'm just saying that it's unlikely. Now, it is a large amplitude here, it is a high voltage, and so amplitude only matters if there's enough energy in order to be able to knock something loose. This has gone into more detail in what is known as the photoelectric effect. And there is, I believe, a separate video for that, and if not, there should be. Photoelectric effect. So I would recommend that you check that out. It was the big evidence that photons exist, and the fact that it's not, we can't treat electromagnetic radiation the same way that we can treat any type of wave motion. Because for mechanical waves, the bigger the amplitude, definitely the more energy. For electromagnetic radiation, not necessarily. Now, we have a power plant that produces power at voltages around 14 or 22 kilovolts. Those are sort of the two numbers that I saw. It goes through a transmission substation, the generator transform, and gets kicked up to high voltage. And this is basically the range that I have seen from various sources. How much you crank it up really depends upon several factors, and it seems to be regulated by state. And then it travels through a great number of lines. How far does it, so how much you crank it up depends on how far it needs to travel. So it goes through however many hundreds of miles or tens of miles. It goes to a power substation, just as it gets closer to the city or to residential sections. So it goes through a switch tower, a main transformer, and then a distribution bus. So it basically comes down and then gets kicked out. Then it goes through the power poles, and at the power poles, it's looking at 7.2 kilovolts to 33 kilovolts. Then it goes through, right before it goes to the house, a transformer drum, and that's when it kicks it down to 120 or 240 volts. And the transformer drum then comes into the meter at your house or home or apartment. Then through the service panel. In our house, this is the place where we flip the breakers when we get a power surge, and then into the rest of the home. And I believe the dryer runs on 240, potentially the air conditioning also. Taking a look at the resistance involved, because there really are three things that we can change in order to change the resistance. Let's hit the simple ones. Area. Yeah, the greater the area, the less resistance. We could definitely, that would be a nice way to do it, except for the fact that if I increase the radius by 41%, I double the price of the wire. And, there is a cost benefit analysis going on here. L is determined by how far away the power plant is from the consumer. And then the material comes down to what you want to use there. And these are the top 5 in terms of resistivity. So silver, obviously incredibly expensive. Gold, incredibly expensive. Copper is becoming expensive. Aluminum is the cheapest, not the best material. So that is 1.68 versus 2.65. So aluminum has a resistivity that is almost 58% more than copper. Aluminum is cheaper. And there's also some thermal properties that need to be taken into account. And I think that's about it. The transformer.